In the last two recordings, I developed the theory for, sorry, I forgot to do something again. In the last two recordings, I developed the theory for the equivalent capacitance that you obtain when you wire together multiple capacitors in a circuit in two different situations. One was if the capacitors are wired together in parallel with each other, and again, future discussion, I'll talk about what that means in more detail, but usually it's clear from the circuit diagram whether you have parallel or series or not. And the other one is if, as I was just saying, if your multiple capacitors are wired together one after the other in series. Okay, and what we found was that when the capacitors are wired together in parallel, the equivalent capacitance is obtained simply by adding the individual capacitances up. Again, of course, capacitor being a constant, it's just a scalar. And in series, what you have to do is you have to take the reciprocal of each of the individual capacitances, add those reciprocals up, and then finally take the reciprocal of that final sum. Okay, again, especially here, there's some it's really easy common mistakes to make, and they're just totally unnecessary. And so I will point those out to you, make sure that you don't make them yourself. All right, so here's our first example, and I wrote it out before starting the recording, so you probably want to pause the recording so you can write this down in your notes or whatever. Okay. All right, presumptively you've done that. So yeah, so we have two capacitors. We've wired together in series. A 4 microfarad, micro is 10 to the minus 6 farads in this case. 2 microfarad capacitor and a 4 microfarad capacitor. And then we've wired together in series with an 18-volt battery. And so how much charge do we get to store in each one, and what's the potential difference across each one? So these are series. And so let's think it through. Let's start thinking through the physics a bit before we start rummaging around for equations. I warn you, here's the first pro tip on this topic. It is the worst mistake you could make in these kind of problems is to immediately start equation hunting. You'll look at this and you're going to be tempted to say, "Oh, there's series. Boom! I'm going to go right to here. Then I don't have to think about anything." And I guarantee you, if you do that, you've got at least a 50% chance of getting the problem wrong one way or another. And the reason for that is these problems are too simple. And yes, I'm serious. What I mean by that is you're going to be these problems are so simple you're going to be tempted to simply plug and chug here. Without thinking about what's going on with the charges and why the capacitors are doing what they're doing, and so that if in a part B or part C I do something different with these now charged capacitors, you're going to be at a loss for what's going on. You've got to think through the physics before you start plugging numbers into equations. Okay, so let's do that. All right, since they're wired together in series, based on the argument that I made in the previous lecture, that means that both capacitors are going to end up storing the same amount of charge. Okay. Remember, the essential idea was this: as one of the capacitors charges up, it steals charge from the other capacitor to which it is physically attached, and so you end up getting the same amount of charge on all. On both capacitors, on all the series capacitors, but the consequence of that, the price you pay for that, is that the potential drop across the capacitors is going to be different. In short, the capacitances are different, the charge that they each store is the same, and therefore it follows logically that the potential drops across the capacitors have to be different. All right, so we expect that the final answer for the charge is that they'll both have the same charge, so let's do that. So first of all, for charge, so I'm writing in words I'm writing down what I just said in words. But you cannot simply calculate you can't say, oh well, since the charge is the same on both, I'll just calculate the charge in one of them and just say the other one is the same. And the reason for that is because yes, you know what the capacitance is of each of the capacitors, but you don't know what the potential drop is across each capacitor. Those are different. It is not 18 volts across both of them. I mean, each one at a time. It's not 18 volts across C1 and also 18 volts across C2. Okay, so instead what you have to use uh, is that the charge that each one gets is the equivalent capacitance multiplied by the total potential drop, which is 18 volts in this case. Okay. So now we need C equivalent. Since these things are wired together in series, the equivalent capacitance is related through the sum of the reciprocals. In this case, there's just two capacitors, so 1 over C1 plus 1 over C2. Okay. And if you like to fiddle around with algebra and put this, get rid of the fractions and everything, you can do that if you like. I'm a little too lazy for that, so I'm going to say C1. It doesn't matter which one you call C1. It's called the 2 microfarad one, C1. So C1 is 2 microfarads. C2. You know what? I should stop here, and I should probably make a drawing. I should have done this before. I apologize. So let's do that. This in your notes, and I'll do better next time. This diagram, this circuit schematic I'm about to make should go before the calculations. So we have an 18-volt battery, and we have C1, and we have C2. Call this one 2 microfarads, and this one 4 microfarads. Okay, good. So returning over here now, 1 over C1 plus 1 over C2, 4 microfarads. And again, I'm going to be lazy. I'm going to stick with microfarads rather than converting to SI units. And so common denominator here, so this is 1/4, this is 2/4, so 3 over 2 microfarads. And yes, I know this math is trivial, but there's a point that I'm going to make here. Sorry, this should be 3 over 4. 4 microfarads, 2 over 4. I'm getting ahead of myself. So this is 3 over 4 microfarads. Now, here's the first place where you may go wrong. Please notice very carefully that we're dealing with reciprocal capacitance, and so the units are in the denominator. This is a completely common and completely unnecessary error. This is an unforced error, as we say in baseball. The units are crucial. You've got to keep track of them because we are dealing with 1 over C equivalent. Very common mistake is to accidentally put these units, when you do this calculation, if you leave the units out, it's really common to write this as I have 1, what I'm about to do is wrong, so don't do this. In fact, just watch it. If you insist on writing it on your piece of paper in your notes, write it and circle it in a big red pen and put a big red star next to it and say wrong in capital letters. Okay, it's really common to do something like this: 1 over C equivalent, and then you say it's equal to 1 over C1 plus 1 over C2. It's equal to this, or and you 3 or 4 layers of equations, and you eventually end up, and especially if you're sloppy, and if you just said 1/2 and 1/4, and you say that's 3/4, and you write this as 3/4 microfarads, and you say, okay, there you are, But look what happened to the units, right? You accidentally threw them into the numerator, and then you say, oh, that's equivalent capacitance, and that is wrong. Okay, so that's a completely unnecessary mistake. It's very elementary and very, very common. Okay, you get so hung up on doing path integrals in this class that you forget, how to do basic math. So watch for this completely avoidable mistake. Please don't do it. Okay, pause recording, make sure you copy that down. I'm going to erase it now. 3, 2, 1. No, the correct answer is, of course, over here, that this is 1 over C equivalent, which gives that the equivalent capacitance is 4/3 microfarads. That's the equivalent capacitance. That isn't the answer that we want. That's not the question that we were asked, but we need that information in order to answer the questions. How much charge is stored? So Q now is equal to C equivalent times V. C equivalent is 4/3 microfarads times 18 volts. And because I am too tired to do math in my head, that works out to be 24 microcoulombs. Okay. Now, that's how much charge is stored in a single one of these two capacitors. So a total charge of 48 microcoulombs. Right. That we weren't actually asked that question, but why not? Okay, and the other question was, did I calculate the charge in each capacitor? We've done that, and the potential difference across each. Okay, I said earlier, let me do that again, and the potential difference across each capacitor. Okay, I said earlier that the potential drop is not going to be 18 volts across each, very different from that. Okay, and in fact, we're going to have a potential drop here, and then we're going to have another potential drop here, and this potential drop plus that potential drop will be 18 volts total. Okay? We expect that to happen. Let's see. So let me label this here. So we're going to have a potential drop across here of V1. We'll have a potential drop here, V2. These are related. V1 plus V2 has to equal V, that is to say 18 volts. Okay, and so therefore, these potentials are trivial to calculate. Again, Q equals C times V, solving for V. Different potentials, same charge, different capacitances. So we have 24 microcoulombs on each capacitor, and the capacitance of C1, is 2 microfarads. You'll notice this is why I was able to leave the micro in, because it's going to divide out anyway. So 24 over 12 coulomb per farad is a volt. 24 divided by 2, so that's 12 volts. And V2, again, same charge, 24 microcoulombs over C2. This answer, V2, had better come out to be 6 volts, right? Because our total potential drop is 18 volts. We've already got 12. We need 6. And it does, in fact, work out. 24 microcoulombs over C2 is 4 microfarads. And so 24 over 4 is, in fact, 6 volts. So that worked out. So yay for that. Okay. A couple of points that I want to make. And I sort of hinted at it right there. But this last thing that I said, that this potential drop plus that potential drop has got to equal the potential drop supplied by the battery, that is an example of conservation of energy in the form of conservation of electric potential, which, as you know, is trivially related to potential energy. So the statement that these two potential drops has to equal the total potential drops by the battery is simply a more or less direct application of conservation of energy. Okay, this is something we're going to see several more times before we're done with circuits. Another recording coming.